Problem number 1. Select if any reaction is not likely happening inside the clean and eliminate from the table. Well, the first reaction is reaction E because the clinker has to be pure with no contamination of magnesium or other minor materials, and in an ideal world the only byproduct of clinker that reflects any wavelength of light is C4AF, which is tetracalcium ferroaluminate, and as the clinker is white it must not contain any of this tetracalcium ferroaluminate. The second reaction that is not taking place is B, because the presence of iron allows for impurities to be mixed in the clinker, and white clinker will now reflect different wavelengths. Problem number 2. Calculate the enthalpy of formation at 288 Kelvin for each of the remaining reactions. Well, this is basically the product minus the reactant. So, for example, in A, we have the kaolinite. We get this information from the table, and we have the quartz, which appears twice, so we multiply it times 2, and the information from the table, alumina from table, and H2O, water, we also get from table and times 2, and you get the enthalpy of formation at 288 K. And that's the same for A, C, D, F, and G, since B and E were cancelled in the question before, in question number 1. So for example, here we have the belite, the CO2, the calcite, and the quartz. You just apply the same formula and you get the answer. Question number 3. Calculate the total enthalpy change for each reaction, assuming that the reaction occurs at the temperature given in the third column of the table. Well, this is basically using first the answer we got before in number 2, in question number 2. The enthalpy of formation at 288 K plus the integral from 288 to the T, which appears as TRXN in the given table in Kelvin, of the sum of the CP of the product minus the sum of the CP of the reactants. And the CP, the way to get it is the sum of A plus B times T plus C times T squared, and you can find A, B, T, and CT squared also given in the table. So for example, the answer of A was 139.3, so we put it right here, plus the integral of 288 to the given value, that is 798. The integral of the CPs of CO2 plus the CP of Al2O3 plus the CP of H2O, which is 113.2 kilojoule over mole, and that's basically the same for everyone, for every other, and except for D, in which you are already given the value of 1900 kilojoules over mole. Question 4. Transform the total enthalpy change to kilojoule per kilogram of clinker using the conversion factor given in the 5th column of the table. Well, it's basically a transformation from kilojoules over mole to kilojoule over kilogram of the change in enthalpy. So we have a conversion factor given for each letter here. So we only use the previous answer, number 3, the total enthalpy change, which is in this column, multiplied by each given conversion factor, and we get that delta H total in kilojoule over kilogram. And for question number 5, we just have to sum this column and we get the total enthalpy of the reactions, which in this case is 1836.1 kilojoule over kilogram. Problem number 6. What is calorific value for a fuel? Well, it's the amount of heat produced by the complete combustion of a specified quantity of a fuel. Problem number 7. If petroleum coke is used in the clinkerization process, how many metric tons of this fuel are required per hour TPH to complete the process? Well, we know that the energy of clinkerization equals the energy of petroleum coke. So we have the 30 tons of raw material per hour. We change them here from ton to kilogram. Then we do the conversion from the mass of raw material to the mass of the clink. And we multiply it times our answer of number 5, the total enthalpy, which is 1835.78, and all of this is equal to 30,000 kilojoule over the mass of coke times the mass of coke. So the mass of coke is equal to the simplification of this part over the 30,000, which gives us 1184 kilograms per hour, but the problem asks us to put it in TPH, so we do conversion from kilogram to tons, and we get that it's 1.18 tons per hour. Problem number 8. If reaction G occurs at 1633 Kelvin and assuming the clinkerization process stops at the temperature, what is the final phase expected for C2S, belite? Assume there is only CaO and CiO2 in the system. Well, the final phase of the clinker production is C3S plus alpha prime minus C2S, and according to part 1 of the project, the composition of CO2 lies between 6 and 15.9%. Using the phase diagram and the two known conditions, which are the temperature 1633 Kelvin and the CO2 composition between 6% and 15.9%, the final composition is C3S plus alpha prime minus C2S. Question number 9. On the ternary phase diagram of the next page, shade the region of CaO, SiO2, Al2O3 system that corresponds to white clinker. Well, we know that the white clinker is composed of approximately 60 to 70% of CaO, 10% of Al2O3, and about 20 to 30% of CiO. So this is how the graph looks like. Problem number 10. Mention at least 2 reasons that could force engineers in a cement plant to take the decision of increasing or decreasing the TPH of petroleum coke required for this kiln. Well, first of all, petroleum coke is a very good fuel for fueling the cement production. It is cheap to manufacture and releases a high amount of heat when burned compared to other coals and fuel sources. This can make producing clinker much more cost effective. However, this advantage comes as a cost. There are some health effects when carbon dioxide and sulfur are released into the environment. Petroleum coke releases 10% more carbon dioxide when burned than general coal used for the same applications. The low-quality petroleum coke has an increased amount of sulfur and can severely affect human and animal health. These are two big controversial topics surrounding the use of petroleum coke.